The cosmic web and the neural network share mathematical properties at a level beyond what simple coincidence would predict. Both have roughly the same fraction of their total matter in nodes versus filaments. Both show similar small world network properties, meaning any 2 points in the network are connected through a surprisingly small number of intermediate links. The researchers were direct in stating that this similarity does not imply any causal connection. The universe is not a brain. The mathematical convergence reflects the fact that both networks are shaped by a small number of universal principles: gravity, pulling matter to nodes, while tension along filaments distributes it, mirrored in biology by the branching geometry of axonal growth. But the visual resemblance and the quantitative overlap have a practical scientific value beyond their philosophical resonance. Understanding the cosmic web structure means understanding where dark matter concentrates, how gas flows between galaxies, and why galaxies in filaments evolve differently from galaxies in void interiors. Webb's detailed imaging of early cosmic web segments is now being used to test models of dark matter distribution directly. The thickness of filaments, the density of nodes, and the size of voids all carry information about the physical properties of dark matter that cannot be extracted from lower resolution data. Early results from this analysis are adding to the tension already identified in the dark matter problem. The filaments Webb resolves in the early universe appear smoother and more uniform than cold dark matter simulations predict. The nodes are denser. The overall topology of the web at early cosmic times looks different from what simulations built on standard assumptions produce. The cosmic web is the skeleton of the universe, and Webb has shown that skeleton was already nearly fully assembled at a time when the standard model says it should have been little more than a framework of loosely scattered bones. What was moving along those filaments into the forming galaxy clusters? What chemistry was riding the cosmic web into the earliest galaxies? Is something Webb caught in its data. And what it found there was the last thing anyone expected to see so early in the universe's history. Building complex molecules requires specific ingredients in specific conditions. You need heavier elements like carbon, oxygen, and nitrogen, which themselves require at least one generation of stars to have lived and died before they can exist in any meaningful quantity. You need enough time for those elements to cool, combine, and form bonds. And you need environments stable enough for fragile molecular structures to survive without being torn apart by radiation. The early universe had almost none of those conditions. It was hot, violent, radiation-drenched, and chemically primitive. The first few 100 million years should have been a near-total desert for complex chemistry. Webb found water, not in a nearby star-forming region, not in a relatively recent galaxy, in stellar nurseries embedded in galaxies so distant that their light left before the universe was 1 billion years old. Webb's infrared spectrometer picked up the unmistakable absorption signatures of water vapor and, in several cases, organic molecules including carbon monoxide and carbon dioxide, in environments that chemistry models had not predicted would support them. The detection of water vapor in early stellar nurseries is confirmed. Multiple independent teams have verified the spectroscopic signatures. The debate is not whether the water is there. The debate is how it got there so fast. To produce water in space, you need hydrogen, which was abundant from the Big Bang, and oxygen, which requires stellar nucleosynthesis to create. Oxygen forms in the cores of massive stars and gets released into the interstellar medium when those stars explode. For oxygen to reach the concentrations needed to produce detectable quantities of water vapor in a stellar nursery, at least one generation of massive stars must have already completed their entire life cycle in that region. In the early universe, at the distances Webb is probing, the timescale available for that stellar generation to form, live, and die before the water signal appears is uncomfortably tight. Models of early chemical enrichment suggest it is possible under optimistic assumptions about how quickly the first stars formed and how efficiently their explosion products mixed into surrounding gas. But the observed abundance of water in some of these early environments pushes at the upper limits of what those models allow. The organic molecule detections are even more provocative. Carbon-bearing molecules of moderate complexity detected in early stellar nurseries by Webb are the chemical precursors to the building blocks of life. They form on the surfaces of dust grains and survive in the cold, dense cores of gas clouds. Finding them in the early universe means the chemistry that eventually led to amino acids and nucleotides was beginning to take shape far earlier in cosmic history than the standard chemical evolution timeline predicted. This does not mean life existed in the early universe. The conditions required for life involve a long chain of additional steps beyond the presence of organic precursors. But it means the chemical foundation was being laid billions of years earlier than most models assumed, and in far more places simultaneously. A universe that is chemically primed for complexity, earlier than expected, is a universe that has had more time to develop that complexity than we calculated. It feeds back, quietly but persistently, into the age problem, the formation timeline problem, and the growing sense that the universe's history is richer and deeper than the standard model describes. And somewhere in that chemically rich early universe, Webb captured a galaxy doing something so energetically extreme that it should have destroyed itself. But somehow, impossibly, it held together. Star formation is not gentle. Each new star ignites from a collapsing cloud of gas under gravity. When it ignites, it blasts radiation outward in every direction. That radiation heats the surrounding gas, pushing it away, making it harder for the next collapse to happen. Stars regulate their own birth rate through this feedback. Too many stars ignite at once, and the radiation pressure clears the nursery, shutting down further formation until the gas cools and falls back in. This self-regulation is a feature of every well-tested model of star formation. It is why galaxies like the Milky Way form stars at a modest, sustained pace rather than in one catastrophic burst. Webb found a galaxy in the early universe, forming stars at a rate that should have triggered runaway feedback and blown the galaxy apart. The object, detected at a redshift placing it in the first billion years of the universe, was converting gas into new stars at a rate roughly 1,000 times higher than the Milky Way's current rate. 1,000 times. The Milky Way produces roughly 1 to 2 new stars per year. This galaxy was producing the equivalent of 1,000 or more per year, sustained over a period long enough to build the stellar mass Webb measured. At that rate, the combined radiation from newly formed massive stars should have created a radiation pressure strong enough to expel the remaining gas from the galaxy in a relatively short time. Standard models of stellar feedback predict that rates this extreme should be self-terminating quickly. The galaxy should have blazed brilliantly for a brief period and then gone quiet as its fuel reservoir was evacuated. Webb found evidence that this galaxy had maintained its extreme rate long enough to build a stellar mass far larger than a brief burst would produce. It had not torn itself apart. It had sustained the burn. Several explanations are under active consideration. One involves the geometry of gas inflow. If cold streams of gas were continuously replenishing the galaxy's fuel supply along filaments of the cosmic web, the inflow rate might have matched or exceeded the outflow rate from stellar feedback, keeping the system in a sustained high-efficiency state. This is consistent with the cold stream accretion idea discussed in the context of disk galaxy formation, and Webb's imaging of nearby cosmic web filaments makes this scenario more plausible than it once seemed. A second explanation involves the physical conditions of the gas itself. In the early universe, gas clouds were warmer, more turbulent, and denser than typical star-forming regions today. Under those conditions, some theoretical models predict that stellar feedback is less effective at dispersing the cloud because the cloud's own gravity more easily overcomes the radiation pressure. The galaxy's gas simply refused to leave. A third possibility, more uncomfortable, is that the models of stellar feedback in the early universe are systematically wrong at extreme star formation rates. If feedback efficiency drops at very high rates, either because the geometry of radiation escape changes or because the timescale for feedback to operate is longer than assumed, then galaxies in the early universe could sustain intense bursts far longer than current models allow. Whatever the mechanism, the galaxy survived its own fire, and the light from that fire has been traveling toward us for over 13 billion years. Something about the early universe allowed its galaxies to build themselves with a ferocity that modern galaxies never match. The conditions that permitted that ferocity are not fully understood, and one of those conditions may connect to an anomaly that does not sit inside any single galaxy or cluster, but in the structure of space itself. The oldest light in the universe is called the cosmic microwave background. It is the faint thermal glow left over from a moment roughly 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form, and the universe became transparent for the first time. Before that moment, light could not travel freely. After it, light streamed outward in all directions, carrying a snapshot of the universe at that instant. That snapshot is extraordinarily uniform. The temperature of the cosmic microwave background varies across the sky by only about 1 part in 100,000. For a universe born in the violent chaos of the Big Bang, this smoothness is itself a remarkable fact, explained by a process called inflation that smoothed out extreme variations in the universe's first fraction of a second. But the map of the cosmic microwave background has one feature that does not fit neatly into any standard explanation. Roughly in the direction of the constellation Eridanus, there is a region substantially colder than its surroundings. significantly colder. A cold spot spanning an area of the sky about 8 times the diameter of the full moon, with a temperature about 70 microkelvins below the average background. In absolute terms, 70 microkelvins sounds tiny. In the context of the cosmic microwave background, it is enormous. Statistical analyses of the background consistently find that a cold spot this large and this cold has a probability of arising by chance of less than 1%. It is almost certainly a real feature of the universe. The standard explanation, tentative and still contested, is that the cold spot corresponds to a supervoid in the foreground, an enormous region of space containing far less matter than average. As cosmic microwave background photons travel through a void, they gain and then lose energy in a specific pattern related to the expansion of the universe during their transit. A large enough void can imprint a cold signature on the background that might account for part of the observed cold spot's temperature. Surveys of galaxy distribution in the direction of the cold spot have identified a possible supervoid, one of the largest known voids in the observable universe. But researchers examining the data have concluded that the void, while real, is probably not large enough or deep enough to fully explain the temperature dip observed. Something additional may be contributing. The more provocative explanation proposed seriously by physicists, and not merely by fringe theorists, is that the cold spot is a bruise, a scar left by a collision between our universe and a neighboring universe in a multiverse, during or shortly after the inflationary epoch, when the universe was still in its first fractions of a second. In inflationary cosmology, bubble universes are predicted to form continuously within an eternally inflating background. If our universe and a neighboring bubble universe were close enough, they could have collided, and the collision would have deposited energy in a specific pattern on our universe's surface. The cold spot's location and profile are roughly consistent with what some models of bubble collision predict. Webb's contribution to this mystery is indirect but real. Its deep field images in and around the cold spot region are being used to characterize the large-scale structure of matter in that direction with unprecedented precision, helping researchers map the supervoid more accurately and potentially isolate how much of the cold spot's signal comes from the void versus from something that happened far earlier in cosmic history. The cold spot does not threaten to overthrow the standard model on its own, but combined with Webb's other anomalies, it contributes to a pattern. The universe contains surprises at every scale, from the chemistry of early stellar nurseries to the topology of the oldest light in the sky. And one of those surprises involves marks that may have been left on our universe by something that existed before it did. The careful version of the idea is a legitimate prediction of inflationary cosmology, the same framework that successfully explains the smoothness of the cosmic microwave background and the distribution of density fluctuations seeding all structure. In eternal inflation, the quantum field that drives cosmic expansion produces bubble universes continuously, each inflating into a vast space-time of its own. Our observable universe is one bubble. The theory predicts that other bubbles exist beyond our horizon, regions of space-time we cannot observe because light from them has not had time to reach us. Where the idea becomes testable is in the possibility of bubble collisions. If two bubble universes formed close enough to each other in the inflating background, the boundaries of their spacetimes could have intersected. A collision would deposit energy in a ring-like pattern on the inner surface of our universe's bubble wall, leaving a circular imprint on the cosmic microwave background. Physicists have searched the cosmic microwave background for circular temperature anomalies that could represent bubble collision signatures. Several candidate features have been identified over the years. None has been definitively confirmed, and none has been definitively ruled out. Webb's role in this investigation is to provide complementary data on the large-scale structure of matter in regions flagged as potential collision sites. A bubble collision would not only leave a temperature mark on the cosmic microwave background, it would also affect the distribution of matter in the affected region, potentially creating slight anisotropies in the distribution of galaxies. In 2023, a team used a combination of Webb imaging data and large-scale galaxy survey data to examine the matter distribution in one of the candidate bubble collision regions. The results were inconclusive. The matter distribution showed some unusual features, a slightly higher density of early-type galaxies than average in a roughly circular region, but the statistical significance was not sufficient to claim a detection. This is an area of active research rather than confirmed discovery. The honest summary is that the data is interesting. The statistical signals are real but below detection threshold, and more data is needed before any conclusion can be drawn. What makes it worth including in this story is not the strength of the current evidence, It is the fact that the question is now observationally addressable at all. Webb provides enough resolution and depth to look for the matter distribution signatures of bubble collisions in a way that was previously impossible. Science has graduated from purely theoretical discussion of the multiverse to a regime where at least one predicted consequence of it can be searched for directly. Whether the search finds anything is a different question, and one that will take years to answer with confidence. But while researchers are examining the edges of our universe's possible interactions with others, Webb has been quietly generating data that threatens something closer to home. Something foundational about the age of the oldest objects inside our own universe. And what that data implies about the universe's age creates a paradox so clean and so unsettling that it has its own name. A universe cannot contain something older than itself. That statement is so logically obvious it barely needs saying. And yet cosmology has been wrestling with a version of this problem for decades, a tension that Webb's data has sharpened rather than resolved. The ages of the oldest stars in the universe are estimated through stellar physics. Stars burn hydrogen into helium at a rate determined by their mass. More massive stars burn faster and die sooner. Less massive stars burn slowly and live for an extraordinary length of time. The least massive stars we know of could theoretically burn for trillions of years. The oldest stars in the Milky Way are found in globular clusters, dense spherical collections of hundreds of thousands of stars that formed in the earliest epoch of our galaxy's history. Astronomers estimate their ages by examining the pattern of stars at different evolutionary stages and comparing it against theoretical models of stellar evolution. The oldest confirmed globular cluster stars in the Milky Way carry estimated ages of around 13 to 14 billion years, with error bars of roughly plus or minus 1 billion year. The standard age of the universe is 13.8 billion years. Overlap with comfortable margin. No crisis, under the standard numbers, but Webb has begun producing more precise measurements of stellar populations in globular clusters, both in the Milky Way and in nearby galaxies, and several of these updated measurements have pushed estimated cluster ages toward the high end of the existing error bars, closer to 14 billion years, in ways that make the margin of comfort uncomfortably thin. A universe aged 13.8 billion years, containing stars aged 14 billion years, is technically impossible. Even setting aside margin of error arguments, having the oldest stars in the universe pressing right against the age of the universe itself leaves no room for the time required between the Big Bang and the formation of those stars. Stars do not form instantly. The universe had to cool, dark matter had to clump, gas had to collapse before the first stars ignited. That process takes time, hundreds of millions of years at minimum. If the oldest stars are truly close to 14 billion years old, and the universe is truly 13.8 billion years old, there is a gap of hundreds of millions of years that simply does not fit. The current scientific position is that measurement uncertainties in stellar age estimates are large enough to prevent this from being declared a definitive contradiction. The stellar physics models used to estimate ages rely on assumptions about initial chemical composition, helium abundance, and the physics of convection inside stars. Small changes in those assumptions can shift age estimates by meaningful amounts. Webb is refining those measurements. Better infrared photometry of globular cluster stars produces tighter constraints on the stellar evolution models. As those constraints tighten, the age estimates either become more comfortable, settling below the universe's age with clear margin, or they remain stubbornly high. The preliminary trend from Webb's most recent globular cluster observations is not toward comfort, it is toward persistence of the tension. If the stars' ages are confirmed to genuinely challenge the universe's age, the most conservative resolution is a slightly older universe, consistent with the concerns raised by Webb's early galaxy findings and the Hubble tension. A universe a few billion years older than the standard model says would comfortably accommodate its oldest stars. And a slightly older universe, with more time for complexity to develop, brings us directly to the most personal question Webb has addressed so far. One that concerns not the distant past of cosmic structure, but the possibility of something alive within it. For most of human history, asking whether life exists elsewhere in the universe was a philosophical question. Webb turned it into a chemistry problem. The James Webb Space Telescope can analyze the atmospheres of planets orbiting distant stars. When a planet passes in front of its star from Webb's perspective, a tiny fraction of the star's light filters through the planet's atmosphere before reaching the telescope. Different molecules in the atmosphere absorb different wavelengths of that filtered light, leaving specific dips in the spectrum. Webb reads those dips the way a fingerprint scanner reads ridges and grooves. In 2023, a team analyzing the atmosphere of a planet known as K218b reported a detection that generated immediate global attention. The planet, a sub-Neptune-sized world orbiting a red dwarf star roughly 120 light-years from Earth, showed spectroscopic signatures consistent with the presence of dimethyl sulfide in its atmosphere. Dimethyl sulfide is a molecule with an unusual distinction. On Earth, it is produced almost exclusively by biological processes. Marine phytoplankton generate the vast majority of Earth's atmospheric dimethyl sulfide. No confirmed abiotic, meaning non-biological, process is known to produce it in significant quantities in a planetary atmosphere. The team was extremely careful in how they reported this. The detection was described as tentative, requiring confirmation by additional observations. They explicitly avoided claiming detection of life, and instead framed the result as a signal warranting urgent follow-up. The statistical confidence of the detection was in a range that could still represent noise or an instrument artifact, and the possibility of an unknown abiotic source producing the molecule on this particular world was acknowledged. Follow-up observations using Webb have been approved and conducted. Analysis of those additional datasets is ongoing as of early 2006, and the scientific community is awaiting confirmation with unusual collective attention. What makes this more than a tentative single measurement is the context Webb has established. The atmosphere of this planet also showed confirmed signatures of carbon dioxide and methane simultaneously. On Earth, the coexistence of methane and carbon dioxide in a planetary atmosphere is chemically unstable. Methane breaks down in the presence of carbon dioxide without a continuous replenishment source. Life is one possible replenishment mechanism. Ongoing geological activity is another. The atmosphere of this planet is chemically active, out of equilibrium in ways that demand explanation. Webb has not found life. That statement carries the full weight of scientific precision it requires. But it has found a planetary atmosphere that behaves in ways that life would explain, in a world within reach of follow-up study, using a method that can be repeated on dozens of additional planetary candidates already in the observation queue. The search for life has moved from speculation to measurement. And the measurement, however uncertain, is the most significant data point humanity has produced on the question. But to understand the full implications of what Webb is finding in planetary atmospheres, you need to understand what it confirmed about a world that makes Earth look hospitable, a planet where even the rocks are airborne. The planet astronomers call a hot super-Earth, orbiting a star 50 light-years from Earth, is one of the most hostile environments Webb has studied in detail. Surface temperatures on the day side exceed 2,000 degrees Fahrenheit. The rock that forms the planet's surface does not simply sit there baking. At those temperatures, silicate rock, the same kind that makes up Earth's mantle, vaporizes. The planet's entire surface is, at least on its permanent day side, a magma ocean releasing mineral vapor into the atmosphere. That vapor rises, cools slightly at higher altitudes, and condenses back into solid mineral particles that fall toward the surface as rocky precipitation. It rains rock on this world. Webb confirmed this atmosphere in 2020 in one of its first exoplanet observations, a result that demonstrated the telescope's atmospheric characterization capability with dramatic clarity. The infrared spectrum of the planet during secondary eclipse, when it passed behind its star, showed the thermal emission profile expected from a rocky body with a silicate-rich vaporous envelope. This was the first direct atmospheric detection of a rocky planet of this type. Previous observations had indicated the planet had no thick gaseous atmosphere, like Jupiter or Neptune. What Webb revealed was a thin but real envelope of vaporized rock and mineral compounds sitting above the molten surface. The scientific value of this detection goes beyond its immediate strangeness. Rocky planets in this temperature regime, known as lava worlds, serve as natural laboratories for understanding the geological and atmospheric evolution of terrestrial planets more broadly. The processes operating on this world, volcanic outgassing, atmospheric erosion by stellar radiation, condensation chemistry in a mineral vapor, are extreme versions of processes that operate more gently on Earth and other rocky worlds. Understanding them at this intensity allows researchers to build better models of how rocky planet atmospheres form and evolve over billions of years. Those models feed directly into the search for habitable worlds, because understanding what destroys habitability helps define the conditions that preserve it. The detection also demonstrates something practically important about Webb's observational power. This planet is small, rocky, and orbiting a relatively nearby star. Webb resolved its atmospheric signature clearly. That means Webb can, in principle, characterize the atmospheres of many other rocky worlds in the coming years, including several in the habitable zones of nearby stars. The queue of habitable zone rocky planets awaiting atmospheric characterization by Webb includes more than a dozen candidates. For several of them, the detection of any substantial atmosphere at all will be scientifically significant. For one or two, the chemistry that Webb might find could be profoundly difficult to explain without invoking biology. The next decade of Webb observations will not merely catalogue distant galaxies and ancient chemistry. It will, observation by observation, build or dismantle the case for life beyond Earth. And while Webb looks outward at new worlds, it has also been looking inward at the ends of stellar lives, capturing images of dying stars so detailed that they shattered models researchers had trusted for generations. A star does not simply go out. When a star similar to our own reaches the end of its life, it expands into a red giant, swelling to hundreds of times its original size before shedding its outer layers in a slow, glowing exhalation of gas and dust, called a planetary nebula. What remains at the center is a dense, cooling ember called a white dwarf. Astronomers have observed planetary nebulae for centuries. They appear in ground-based telescopes as beautiful, symmetrical rings and shells of glowing gas, sometimes circular, sometimes elliptical. The standard model of how they form, the stellar wind theory, predicted that the shedding of a star's outer layers should produce relatively smooth, ordered, expanding shells. Webb looked at the Southern Ring Nebula in 2002 and produced an image that forced a complete reassessment. The Southern Ring Nebula is a planetary nebula roughly 2,000 light-years from Earth. In earlier telescope images, it appeared as a pair of nested oval shells with a bright central star, beautiful and reasonably consistent with standard models. Webb's infrared imaging revealed a completely different interior structure. Inside the smooth outer shells, Webb detected a chaotic network of arcs, spurs, and concentric rippled structures that no standard model of planetary nebula formation had predicted. Some of the structures resembled the wake patterns left by a boat moving through water, suggesting the gas was being shaped by something moving through it. Others showed layered rings that imply the star shed its mass in discrete pulses, rather than in a continuous flow. The research team analyzing Webb's Southern Ring Nebula data identified evidence that the central white dwarf had a companion, a second star orbiting it during its death process, and that the gravitational interaction between the dying star and its companion had sculpted the ejected gas into the complex geometry Webb revealed. The ripples and arcs were not random. They were the record of an orbital dance between two stars playing out over thousands of years as one of them died. This finding has broad implications. If companion star interactions are responsible for the complex morphologies Webb is revealing inside planetary nebulae, then the standard single-star model of nebula formation, which has guided stellar evolution theory for decades, represents only the simplest case. The majority of stars in the galaxy exist in binary or multiple star systems. Their deaths may routinely produce the kind of complex, dynamically sculpted nebulae Webb is finding, rather than the smooth shells single-star models predict. Stellar evolution models used to estimate the chemical enrichment of the interstellar medium, the amount of carbon, oxygen, and other elements that dying stars return to the galaxy, may need systematic revision. If dying stars in binary systems eject their outer layers differently than single stars, the chemistry of the next generation of stars and planets forming from that material changes accordingly. Webb has turned every dying star it has examined into a puzzle that the existing models solve only partially. And among those dying stars, one produced something that stopped the research team cold, a time-delayed replay of its own death, preserved in light and still unfolding today. Light echoes are among the strangest phenomena in observational astronomy, and Webb captured one in unprecedented detail. When a star explodes or undergoes a dramatic brightening event, it releases an enormous pulse of light in all directions simultaneously. Most of that light travels directly towards observers, but some of it travels at an angle, hits a nearby cloud of dust, and reflects toward us along a longer path. Because it traveled a longer distance, it arrives later. The result is that observers on Earth see the original stellar event directly, and then, months or years later, they see a ring of reflected light expanding outward from the star's position. The ring moves faster than the speed of light. In apparent terms, though nothing is actually moving at that speed, the expansion is a geometric effect, the illuminated circle sweeping across the dust cloud as the light pulse moves through it. Webb captured a light echo from a variable star in the Milky Way, with a clarity that previous instruments could not match. The star, known to undergo periodic outbursts, had produced an outburst captured in previous telescope data. Years later, Webb imaged the same region and resolved the expanding light echo in multiple wavelengths simultaneously, tracing the structure of the dust cloud the light was reflecting from and the detailed geometry of the outburst itself. By comparing the structure of the echo at different times, the research team extracted a three-dimensional map of the dust surrounding the star. They also used the light echo as a kind of time machine. The reflected light had spent extra time in transit, meaning it left the star at a different point in its outburst cycle than the direct light. By comparing the spectral content of the direct and reflected light, scientists could analyze how the star's output had changed over time during the outburst, using the echo as a delayed recording of an event that had already ended. This technique, called light echo spectroscopy, was theoretically described decades ago, but had never been applied with the precision Webb enabled. The data revealed details about the outburst's temperature, chemistry, and duration that could not be extracted from a single direct observation. The implications extend beyond this one star. Supernovae, the explosive deaths of massive stars, also produce light echoes in the surrounding dust. Several historical supernovae in the Milky Way and nearby galaxies have left dust clouds that still carry the light echo of their explosion. Webb is capable of conducting light echo spectroscopy on those echoes, effectively retrieving the spectrum of a stellar explosion that occurred centuries or millennia ago from the replay still traveling through the surrounding dust. Science does not normally allow you to go back and re-examine events that happened before your instruments existed. Light echoes are an exception, and Webb is using them to read recordings of stellar events that no human observer witnessed directly. What Webb has turned up while reading those recordings, and what it has found when examining the very constants that govern how atoms absorb and emit that light, touches something far deeper than any individual star or galaxy. It touches the possibility that the laws of physics themselves are not the same everywhere in the universe. Physical constants are supposed to be constant. That is why they are called constants. The speed of light, the gravitational constant, the fine structure constant, which governs how strongly charged particles interact with light, and is deeply embedded in the quantum mechanical rules that determine how atoms behave. These numbers do not vary. They are the same in your laboratory, on the surface of a neutron star, and at the edge of the observable universe. That universality is foundational to physics. Without it, the laws of nature as we understand them would not be laws at all. A growing body of observational evidence suggests the fine structure constant might not be perfectly constant across cosmic space. The effect being claimed is tiny, a variation of perhaps a few parts per million across billions of light years. But a few parts per million in the fine structure constant is enough to change how atoms absorb and emit light, and that change would show up in spectroscopic observations of distant quasars. The initial claims of fine structure constant variation came from observations using large ground-based telescopes over a decade ago. Different research teams found different results, some seeing variation, others seeing none. The measurements were difficult to reconcile, and the debate was unresolved. Webb has entered this debate by providing spectroscopic data of distant quasars at a resolution and signal quality that previous instruments could not reach. The fine structure constant leaves its signature in the precise spacing of absorption lines in quasar spectra. The more precisely you can measure those spacings, the tighter the constraint on whether the constant is truly constant. Preliminary analyses of Webb quasar spectroscopy have been published. The results are provocative without being conclusive. Some lines of analysis show no significant variation. Others show hints of variation at a level consistent with earlier claimed detections, at the boundary of statistical significance. The full analysis pipeline for Webb's quasar spectroscopy data is ongoing. The definitive result from Webb on fine structure constant variation has not yet been published as of early 2206. The work is continuing. If variation is confirmed, the implications are extraordinary. A universe where the fine structure constant differs across cosmic space is a universe where the fundamental rules of atomic physics change depending on where you are. Chemistry would operate differently in different regions of the cosmos. Nuclear reactions in stars would proceed at slightly different rates. The entire periodic table of elements would have slightly different properties across space. Life as we understand it depends on specific values of fundamental constants. A universe where those constants vary might contain regions where the chemistry that produced us was more favorable, and other regions where it was less so. This connects directly to anthropic reasoning about why we find ourselves in a part of the universe that supports complexity. The question of whether the fine structure constant varies is one of the most consequential open questions in fundamental physics. Webb's data is the best data yet brought to bear on it. While physicists examine whether the rules of atomic physics hold everywhere in the universe, Webb has been measuring something that underpins the rules of the universe's largest scale structure, something whose apparent behavior is now threatening the longest-standing assumption about how the cosmos will end. In 1998, Two independent teams of astronomers discovered something that shook physics to its core. The universe is not just expanding, the expansion is accelerating. Galaxies are flying apart from each other at an ever-increasing rate, as if something embedded in the fabric of space itself is pushing them. That something received a name: dark energy. Dark energy is the dominant component of the universe. Roughly 68% of all the energy content of the cosmos is dark energy. It does not cluster, does not emit light, and does not interact with matter in any detectable way. Its only observable effect is on the expansion of space itself. In the standard model, dark energy is treated as a cosmological constant, a fixed value, the same everywhere in space and at all times, unchanging across the entire history of the universe, past and future. Webb, combined with data from a massive galaxy survey called the Dark Energy Spectroscopic Instrument, that mapped tens of millions of galaxies across cosmic history, produced results in 22,204 that challenged the cosmological constant assumption. The analysis compared the rate of cosmic expansion at different periods in the universe's history by using a specific class of ancient stellar explosion as standardized distance markers across cosmic time. By measuring how fast the universe was expanding at different epochs, the research produced a map of expansion history from the early universe to today. The result carried a statistical significance of about 3 sigma, a level that scientists consider strong evidence, requiring follow-up rather than definitive confirmation, but enough to take seriously. The expansion history best fit by the data was inconsistent with a perfectly constant dark energy. The data preferred a dark energy value that was stronger in the past and weakening toward the present. If dark energy is not constant, but is instead evolving, becoming weaker over time, it is called a dynamical dark energy model, and it changes everything about the universe's predicted future. Under a cosmological constant, the universe expands forever. Galaxies drift farther and farther apart, until eventually they become unreachable, and the universe ends in cold darkness. This fate is called the Big Freeze, or heat death. Under a weakening dark energy, the future becomes genuinely uncertain. If dark energy continues to decrease, it could eventually reach zero and reverse sign, turning from a repulsive force into an attractive one. Under that scenario, cosmic expansion would eventually slow, stop, and reverse into a contraction. The universe would collapse back on itself. The Big Crunch, or dark energy, could decrease towards zero and stabilize there, leaving a universe that expands more slowly than currently predicted, but never reverses. The 22,004 data was not sufficient to determine which trajectory is correct. It was sufficient to suggest that the trajectory is not the one the standard model has been assuming for 25 years. Webb's continued observations of supernovae and large-scale structure are being used to refine the expansion history measurements. Each new data release tightens the constraints on how dark energy is evolving, if it is evolving at all. If the evolution is confirmed, the rulebook for the universe's future will need to be rewritten. And the image at the absolute end of Webb's observational reach, the deepest image ever taken of the universe, contains something at its edge that may be the strangest thing the telescope has yet encountered. Webb's deep field images are the most profound photographs in human history. In a single long exposure, Webb stared at a patch of sky, smaller than a grain of sand held at arm's length, and captured thousands of galaxies, most of them older than anything our instruments had previously resolved. Some of those galaxies existed when the universe was less than 5% of its current age. Their light has been traveling toward us for over 13 billion years. The images are not just beautiful, they are functional data sets. Every smear of light in the frame is a galaxy with measurable properties: distance, mass, star formation rate, chemical composition. Each one is a data point in the map of cosmic history that Webb is building. In one of the deep field exposures taken in late 2003, a team conducting a systematic analysis of all objects in the field flagged something at the extreme edge of the image's redshift range. An object so distant that its light left before the universe was 400 million years old. At that distance, Webb should barely detect a smudge of light, a few pixels representing the integrated light of millions of stars, barely resolved at the limit of the telescope's capability. What the team found in that region of the frame was a point source, compact, bright relative to expectations, showing a spectral energy distribution, the pattern of brightness across different wavelengths, that did not match any standard category of object in the team's classification system. The object was too bright to be a normal galaxy at that redshift given its compact size. The spectral shape was unusual, brighter than expected at certain infrared wavelengths, and dimmer than expected at others, in a pattern that did not match the template spectra of known galaxy types, known active galactic nuclei. or any class of star in the Milky Way that could plausibly be confused with a background source. The team published their analysis carefully, labeling the object a candidate for an unusual source type and calling explicitly for follow-up spectroscopy. Their paper ran through several possible explanations and found all of them partially unsatisfactory. One possibility is a gravitationally lensed galaxy whose image is being distorted and magnified by an intervening massive object, making it appear more compact and brighter than it truly is. This is a known effect that produces unusual-looking objects in deep field images. However, the team did not find obvious evidence for a lensing mass in the foreground. A second possibility is an unusual type of active nucleus, a quasar or quasar-like object with an atypical spectral shape produced by unusual dust geometry or chemical composition. This remains a viable explanation, but requires properties outside the normal parameter space for known active nuclei at that epoch. A third possibility, discussed with appropriate caution, is that the object belongs to a class not yet catalogued. The early universe likely contained object types that no longer exist or are extremely rare today. Webb is the first instrument capable of detecting them, which means it may also be the first to encounter categories of objects that require new classification entirely. Follow-up spectroscopy of this object is scheduled. The results will either resolve the mystery neatly, fitting the object into a known category with unusual parameters, or sharpen the anomaly into something that demands a new explanation. The deepest image ever taken of the universe contains something that science does not yet have a name for. That sentence alone captures what Webb has accomplished. Step back from the individual discoveries for a moment. Galaxies too massive in the early universe. Black holes too large for their age. A cosmic timeline under pressure. Dark matter behaving differently than expected. Chemistry appearing too early. Disk galaxies forming in conditions that should have prevented them. A Hubble constant that refuses to be measured consistently. Stellar ages pressing against the age of the universe itself. Dark energy that may be evolving. A molecule that life produces, detected in a planetary atmosphere. Dying stars with internal structures no model predicted. An unidentified object at the furthest edge of the observable universe. Every single one of these findings, considered in isolation, could be a measurement anomaly, an edge case, a model that needs minor revision. Scientists know this. They apply the appropriate caution, but the findings are not in isolation. They are simultaneous. They arrived within years of each other from the same instrument, consistently pointing in the same direction. The universe is older, more structured, more chemically complex, and more energetically extreme in its early history than the standard model of cosmology predicted. The anomalies are not scattered randomly around the standard model's predictions. They are clustered. They all describe a universe that assembled itself faster, built bigger structures earlier, maintained more chemical richness further back in time, and evolved on a more complex trajectory than the lambda-cold dark matter model allows. When anomalies cluster in the same direction, that is not noise, that is signal. The lambda-cold dark matter model is the most successful scientific framework cosmology has ever produced. It correctly describes the large-scale structure of the universe. It correctly predicts the pattern of temperature fluctuations in the cosmic microwave background. It matches the observed abundance of light elements from the Big Bang. It works, demonstrably and impressively, across an enormous range of observations. And it is now facing a systematic challenge from the most precise instrument humanity has ever aimed at the universe. The scientific community's response has been measured and serious. Several prominent cosmologists have published papers explicitly acknowledging that Webb's findings collectively constitute a challenge to the standard model, not just isolated puzzles within it. Others have defended the model's resilience, pointing to the error bars, the ongoing confirmations needed for some of the most extreme claims, and the model's continued successes in areas Webb has not challenged. This is science working exactly as it should. The tension is productive. The debate is generating new ideas, new measurements, new theoretical frameworks. Some of those frameworks preserve the core of the standard model, while modifying its ingredients. Others are more radical, proposing fundamental revisions to the timeline, to dark matter, to dark energy, or to the initial conditions of the Big Bang itself. What is certain is that the conversation has changed. Webb changed it. The questions cosmology is asking in 22.6 are different from the questions it was asking in 22,000, before the telescope opened its mirror and looked back to the beginning of time. And in the space opened by those new questions, a new framework is being built right now. What it looks like, and what it means for every assumption humanity has made about the universe it inhabits, is the final chapter of everything Webb has started. Scientific revolutions do not announce themselves with a single discovery. They accumulate. Anomaly by anomaly, confirmed result by confirmed result, until the weight of the inconsistencies forces theorists to step back from the existing framework and ask whether a different foundation would fit the evidence better. Cosmology is in that accumulation phase right now. Several competing theoretical frameworks are being developed in parallel, each attempting to account for the full range of Webb's findings without abandoning the well-confirmed predictions of the Standard Model. Understanding what these frameworks propose reveals how profoundly Webb has shaken the foundations of cosmic science. The first class of new frameworks involves modifications to dark matter, proposals for warm dark matter, fuzzy dark matter, and self-interacting dark matter all modify the behavior of the universe's invisible scaffolding in ways that could accelerate early galaxy formation without destroying the Standard Model's successes elsewhere. These are conservative modifications, changing one ingredient without replacing the recipe. Several groups are running new generations of computer simulations using these modified dark matter models to see whether they can reproduce Webb's early galaxy observations while still matching the cosmic microwave background and the large-scale structure of the nearby universe. Early results from these simulations are promising, but incomplete. Warm and fuzzy dark matter help with some of Webb's anomalies. They struggle with others. The search for a single dark matter modification that fixes everything simultaneously, without breaking anything, remains ongoing. The second class involves modifications to the inflationary epoch, the universe's first fraction of a second, when an exponential expansion smoothed out initial density fluctuations. Standard inflation produces a specific pattern of those fluctuations, called a nearly scale-invariant power spectrum, that the cosmic microwave background observations confirm with high precision. But modest modifications to inflationary models can alter the amplitude or shape of those fluctuations in ways that seed faster early structure formation. If inflation produced slightly larger density fluctuations on small scales than the standard inflationary model predicts, matter would have clumped more efficiently in the early universe, producing more massive early galaxies on a faster timeline. A team published a modified inflationary model in 2023 specifically designed to address Webb's galaxy mass problem, showing that a small enhancement in small-scale power could bring simulated early galaxy populations into better agreement with observations while remaining consistent with cosmic microwave background measurements. The third class is more radical. A growing number of theorists are working on frameworks that revise the fundamental cosmological parameters themselves: the age of the universe, the matter content, the dark energy equation of state, all simultaneously, in a way that preserves agreement with the best measured observations while accommodating Webb's anomalies. These models tend to predict a universe that is somewhat older than 13.8 billion years, has a dark energy that evolves over time, and has a matter content distributed in ways that the Standard Model does not capture. Some of these proposals have names: extended dark energy models, interacting dark sector models, modified gravity frameworks that replace Einstein's general relativity with a more general theory that reduces to general relativity in the regimes we test it most rigorously. None of these frameworks has yet achieved the complete consistency that the Standard Model provides across all observations. Each solves some problems and introduces others. The field is genuinely in a pre-consensus state, exploring the space of possibilities that Webb's data has opened. That exploration is the healthiest possible sign that science is working. A field in crisis is a field that is learning something new. The discoveries Webb make possible are not a failure of cosmology. They are cosmology doing what it is designed to do, pushing into the unknown until the unknown pushes back, and then figuring out what the resistance means. Every anomaly Webb found connects back to a question humans have always asked. Where did we come from? Are we alone? How does this end? The answers that Webb is in the process of rewriting are not abstract scientific curiosities. They are the foundation of everything we understand about our place in the cosmos. If the universe is older than the Standard Model says, then the timeline for cosmic evolution is longer, more time for chemistry to develop, more time for stars to seed the interstellar medium with complex elements, more time for life to have arisen in places we have not yet looked. An older universe does not guarantee life elsewhere in the cosmos, but it expands the window during which life had opportunities to develop. If dark matter behaves differently than the Standard Model assumed, then the structure of the universe at small scales, the scales of individual solar systems and star clusters, may be different from what we have calculated. The distribution of habitable environments in the galaxy, places where rocky planets can form and persist over billions of years, depends on those small-scale structures in ways that are only now being modeled with Webb's observational constraints. If dark energy is evolving, the universe's future is genuinely uncertain. The comfortable prediction of indefinite expansion into cold darkness, which was at least a clear answer, has been replaced by a range of possible futures depending on how dark energy continues to change. The universe might freeze, it might crunch, it might do something no current model describes. If the fine structure constant varies across cosmic space, then the chemistry that makes life possible here is not guaranteed to be possible everywhere. Some regions of the universe might be fundamentally inhospitable to the kind of complex molecular chemistry that biology requires, not because of temperature or radiation, but because the atomic rules themselves are different. That would mean the universe is partitioned, in some sense, into regions that can support complexity and regions that cannot. And if a planetary atmosphere 120 light-years away contains a molecule that life makes, and that signal is confirmed by follow-up observations, then the question, are we alone, will require a different answer than anything previously available. Confirming biology elsewhere, even microbial chemistry around a distant star, would be the most consequential discovery in the history of science. Webb is in the middle of all of these questions simultaneously. It launched as a telescope. It has become the instrument through which humanity is renegotiating its understanding of what the universe is, how old it is, how it will end, and whether it contains others like us. The scientists operating Webb know this weight. Every observation is a vote in a calculation that matters beyond any single career or research program. The data being collected right now in that golden mirror a million miles from home will be analyzed by researchers for decades, each new analysis extracting a deeper layer of what the universe encoded in its ancient light. We are not at the end of this story. We are at the moment when the story changed, when the telescope looked back and found that the universe is not the place we thought we had measured. It is older, stranger, more chemically generous, more structurally ambitious, and perhaps more populated than the model we built to describe it. Every answer Webb has delivered has come with a more urgent question attached, and that exchange, discovery generating mystery generating discovery, is the most honest description of what science is. The golden mirror is still open. The data is still coming, and whatever it finds next will change the frame again. There is a before and an after in the history of cosmology. Before Webb, the standard model of cosmology was in excellent health. It had survived every major observational test. Its predictions matched the cosmic microwave background, the large-scale structure of galaxies, the abundance of light elements, the existence and approximate properties of dark matter and dark energy. Scientists were refining it, not questioning it. After Webb, the standard model is in the most serious empirical challenge it has ever faced. Massive early galaxies, ancient black holes, precocious chemistry, evolving dark energy, a Hubble constant that two independent methods cannot agree on, stars that press uncomfortably close to the age of the universe they inhabit, and an unidentified object at the edge of the observable universe that does not fit any known category. These are not the symptoms of a model that needs a minor update. They are the symptoms of a model encountering the edge of its validity, the regime where it was never tested, and finding that the universe beyond that edge does not behave as extrapolated. This is not a failure of science. It is science at its most alive. Every major shift in our understanding of the universe has followed this same pattern. The universe looked simple and tidy from a certain vantage point, until the instruments became powerful enough to see what was actually there. Newtonian gravity described the solar system perfectly, until Mercury's orbit revealed a discrepancy that required Einstein's general relativity. The universe appeared static and eternal until Hubble measured the recession of galaxies. Cosmic expansion appeared decelerating until Type Ia supernovae showed it was accelerating. Each time, the crisis in the existing model was not a sign that science had failed. It was a sign that science had succeeded in reaching a new level of resolution, close enough to reality to see that the previous map was approximate. Webb has given cosmology a new level of resolution. It has extended humanity's observational reach to within a few 100 million years of the Big Bang, and provided chemical, structural, and dynamic measurements at distances and precision that no previous instrument approached. What it found is that the universe, in its earliest, most formative period, looked different from what the standard model predicts. The differences are systematic. They point in a consistent direction. They demand an explanation that current theory cannot fully provide. The generation of cosmologists working today analyzing Webb's data, building new theoretical frameworks, running new simulations, designing new follow-up observations, is engaged in the most exciting and consequential work in the history of their field. They are standing at the transition point between one understanding of the universe and the next. We do not know yet what the new framework will look like. We do not know whether the universe is 20% older than currently measured, or whether dark matter has properties that will require decades to pin down, or whether the fine structure constant varies subtly across the cosmos, or whether the life-indicating molecule in that distant atmosphere will be confirmed by the next round of observations. What we do know is that Webb will keep looking.